Vanakkam. Welcome to this video on biomechanics. We have been looking at biological materials and mechanics of biological materials or mechanical properties of biomaterials. Specifically, we have been focusing on bone as a biological material. With respect to bone, we studied its microstructure, we studied types of bone, its properties in terms of strength, and we looked at stress strain curves, and we looked at the corresponding engineering materials. We compared the properties of bone with some engineering materials, so we can better place the bone as a biological material for our understanding. In this video, we will be looking at bending of bones, because bending can happen because of force application in such a way that it might sometimes cause fractures. So, an understanding of how bones bend will help us to gain a deeper insight on how fractures happen. This is only the beginning of the study of fractures. So, bending of bones will help us understand or gain deeper insight on how bones fracture, such as when a person slips or when a person is skiing and they fall down. How does bone get fractured? Consider a beam that is having a uniform cross sectional area. That might be an arbitrary cross section, but uniform throughout its length L. It need not be rectangular or circular, but for the sake of simplicity we can assume it to be rectangular or circular. But the point is that it is having an arbitrary but uniform cross section throughout its length L. It is supported at two ends, and a force of F or a load of F is applied at the center of the beam or at L by 2 from either end. In this case, we expect the bone or the beam, in this case the beam, to bend. A force of F is applied here, and the supports provide reaction force of F by 2. How do I know this? You actually do not know this when you start out, but we can quickly solve for this. Let me try to do this. Now, let us assume that that is the beam, and I am applying a force F here, and I do not know the reaction here at this end, which I am going to call as RA, and I do not know the reaction here, which I am going to call as RB, and this distance is L by 2 and that distance is L by 2. Now, this beam as a whole is in equilibrium. That means, for this xy axis as shown in the picture, sigma mz is 0. And let us say that I am taking a moment about the point A, for example. I am taking a moment about point A. So, that would be minus F times L by 2 plus RB times L. Why plus RB? Because RB will cause a counterclockwise moment, because this is sigma mz is equal to 0, counterclockwise considered positive. So, minus F times L by 2 plus RB times L is 0. Divide by L throughout, I will get minus F by 2 plus RB equal to 0, or RB equal to F by 2. Now, if I substitute sigma Fy equal to 0, upgoing is considered positive, RA plus F by 2 is equal to F. This will give me RA as F by 2. Reusing our knowledge of statics or using our knowledge of statics, remember? Okay. So, that is how I know. That is how I know that the reaction forces at the two ends are indeed F by 2 and F by 2. Okay. By now, you should be able to figure this out, but anyway, I quickly solve this for you. Now, Consider this ruler that I am going to use to example or illustrate this concept in beam. Now, let us suppose that I am applying a force in the middle like this, at the center like this. Okay. Now, in this case, this ruler is bending like this, or it is sagging, it is sagging like this. In this situation, you can say that the bottom of the ruler is just a tad bit longer than the top of the ruler, right. Of course, this ruler has a thickness of just 2 mm, very thin ruler. But let us suppose that this is having some thickness, some finite thickness. In that case, what will happen is that as you go from the bottom to the top, right, in the bottom the length will be higher, and in the top the length will be much lower, and somewhere in the middle, not necessarily exactly in the middle, there will be a particular point at which the length before bending and the length after bending will remain the same. This particular line along the length of the ruler or along the length of this beam is called as a neutral axis for this beam. Okay. Now, here is this beam one again. At equilibrium, essentially sigma fx equal to 0, sigma fy equal to 0, sigma mz equal to 0 for the entire beam. Of course, there are no forces in the x direction. The downward force capital F, that is actually in the negative y direction, is it not? Because the xy axis is given as shown. This downward force capital F is countered by two forces F by 2, capital F by 2 at the two supports, right. Now, also because the beam as a whole is in equilibrium, the total moment on this beam is 0. About any axis that you take, the total moment is 0. Remember, for equilibrium, sigma fx equal to 0, sigma fy equal to 0 and sigma m equal to 0 for equilibrium in 2D, is it not? Based on this, I know that sigma fx is 0, sigma fy is 0 and sigma m is 0. Because the beam as a whole is in equilibrium, I know that any section of the beam is also in equilibrium. How do I know? It is not possible for any specific section of the beam to have a different configuration or a different status than the whole beam, right. And because I know the whole beam is in equilibrium, sections of the beam are also in equilibrium. Now, let us consider a section of the beam that is on the right side of this beam as shown. There is a support F by 2 that is there, and we are cutting this beam at a distance of x from the right end. Okay. That is, I am sectioning here at a distance of x from the right end. I am sectioning somewhere here. Okay. If I section like that, remember as I said, the beam as a whole is in equilibrium. That means that that section is also in equilibrium, and all the three equations of equilibrium for 2D apply. What are these three equations of equilibrium? Sigma fx equal to 0, sigma fy equal to 0, sigma m is equal to 0. Okay. Now, that means when I am making this cut, there is a force, this will reveal an internal force in that direction whose magnitude is F by 2. How do I know this? Well, sigma fx equal to 0 or sigma fy equal to 0, That means F by 2 plus some unknown force V is acting in the downward direction. It must act in the downward direction. How do we know that it is acting in the downward direction? I actually do not know. I can assume, but because F by 2 is acting in the upward direction, I am assuming this unknown force V, unknown internal force V is acting in the downward direction. By the way, why do I say that it is an internal force? This section X, this section at X that I am making is not a real section. It is a thought experiment. I am making the cut and the force that is there is an internal force, is a force that is internal to the beam. Okay. When I make this cut, I reveal this force. So, when I say sigma Fy equal to 0, and because capital F load is applied to the left of the beam and I am only considering the right side of the cut, right, I am making a section and I am only considering the right side of the section, right. Because of this reason, only this part of the beam is under discussion now. So, capital F does not come into the picture. So, for that xy axis, if I write sigma Fy equal to 0, F by 2 minus V equal to 0, that means V is equal to F by 2. This V that is internal to this beam is called as shear force. Okay. This is the internal shear force. Also, because this beam as a whole is not rotating or is not undergoing a rotational disturbance, I know that sigma m is equal to 0. I am going to call this point some p. Now, if I take sigma m equal to 0, if I take the moment about this point p, V will not cause a moment at point p. Why? Because the moment arm is 0. Okay. What I also realize is that this when I make this section, it will also reveal an internal moment. I am going to call that as some m, that will come into the picture, and that is a clockwise moment. I am assuming that to be a clockwise moment. So, that would be minus m. F by 2 is a force that is acting at a perpendicular distance of x from p. So, that moment would be plus F by 2 times x is 0. That means m is equal to F by 2 times x. As I said, this is what we have worked out here in this slide. As I said, this shear force V is F by 2 acting downward, and that bending moment m is x F by 2, which is a clockwise moment, right. This is what we have seen. How did we find this? What is the principle based on which we found this? That the beam as a whole is in equilibrium. If the beam as a whole is in equilibrium, that means that sections of this beam are also in equilibrium. Okay. This internal vertical force is called as shear force, and this internal torque is called as bending moment. Okay. Now, it is somewhat clear that as x changes, because I section this here, right. So, depending on x, the shear force and bending moment may change. In this particular case, the shear force does not change. So, it will be useful for me to draw a plot of the shear force as a function of x, as a function of the length where I am sectioning on this beam. Okay. that is this place, that is this diagram. Okay. If P is the applied force, then at this point I am going to have minus P by 2 load, and at this point I am going to have P by 2 load, right. And bending moment we have told is x times F by 2, and at this point at the middle x is equal to L by 2. So, that is the bending moment at the middle is F L by 4. In this case I am assuming a force to be P. So, that will be P L by 4, that will be the maximum bending moment, that is the point where maximum bending happens, that is the point of maximum bending moment. These are relations that we know from statics, that also a principle is that wherever shear is changing direction is the place where you are going to have a maximum or minimum in the bending moment diagram. This is something that we know from engineering mechanics. Maybe that is a bit of a detail for you, but bear with me. I am again, we have done this analysis using first principles. I request you to please check the correctness of this, because I have just done this using first principles and I have drawn this diagram. So, for sections between L is equal to 0 and L is equal to L, everywhere I have drawn this shear force and bending moment diagram, right. Remember, the beam as a whole is in equilibrium. That means that any section that I take in this beam is in equilibrium. Okay. So, to a first approximation, so when I make this bend, so when I take this ruler and when I bend like this, right, to a first approximation the beam deforms to a circular arc of radius r and angle alpha. Okay. So, that is the angle alpha and that is the radius r there. Okay. That is the radius r. At the middle of the axis or the neutral axis where small y is equal to 0, we see what is this point. At this point L is equal to r alpha for small alpha. For very small values of alpha, that length L is actually r alpha. So, that means alpha is L by r for small values of alpha, and this is true, right, because it does not bend a lot, right. The beam does not bend a lot, the values of alpha are very small, much less than 1 radian. Okay. Now, if I want to find out the length of the beam or the length of that point in the beam at a distance of some distance y from this midline, right, y above this midline or y below this midline as the case may be. First we will do the y above this midline, that would be L of y is r minus y times alpha. But then what is alpha? Alpha is L by r, that would be r minus y times L by r. But the original length was, what was the original length? The original length was L. So, that means original length is L, that means deformation. What is the deformation? What is the deformation? Deformation is L of y minus L, and L of y itself we know is r minus y times L by r minus L. After some algebra, this is actually minus of y by r times L. If this is a deformation, then the strain would be minus of y by r. Okay. what would be the stress? Epsilon y is minus of y by r. What is sigma of y? That is, because assuming that this has elastic modulus capital Y, sigma of y would be minus capital Y times small y by r, where small y is the distance above the neutral axis where I am making this measurement. Okay. What is small y? Small y is the distance above the neutral axis where I am discussing, the point of interest that I am discussing. Okay. Sigma of y is capital Y times small y by r. Of course, as I mentioned earlier, the top portion of this ruler is compressed and has a length less than L. The bottom portion of the ruler is elongated and has a length greater than L. Okay. So, the top portion is in compression and the bottom portion is in tension. Okay. Somewhere in the middle you are going to have this neutral axis where the length is equal to L. Now, for the top portion to be compressed, there must be an internal force, right? There must be an internal force at the top in the positive x direction, right? Because that is when the top portion will be compressed. For the bottom portion to be deformed or elongated, to be under tension, the internal force at the bottom must be in the negative x direction, or pulling into the section into the other section like this. So, or like this, right. So, in the top these are the forces, and at this point and along the neutral line the force is 0, and in this point. Now, each of these forces will cause a torque in the z direction, right. Each of these forces will cause a torque in the z direction, because their corresponding momentum will be the corresponding y's, small y's. Okay. And each of this, actually all of this put together, if I sum all of this, they will all put together will cause a clockwise moment. Note, the bottom will also cause a clockwise moment, the top will also cause a clockwise moment, although the forces are in two different directions, they both will cause a clockwise moment, okay, or negative torque. I can sum all these internal torques to arrive at some total internal torque, which I am going to call as tau int. Then the total torque tau z is tau int plus half times f x equal to 0. Now, consider a small area element, a small cross sectional element with an area dA at a distance y from the neutral axis, okay, at a distance y from the neutral axis. Then that point will have an area dA as its width times the distance dy, w of y times dy, where w of y is the width at this point y. What is the force that is acting at this point? We know that force is, because sigma is f by a, I know f is sigma a, is it not? So, this small infinitesimal force that is acting at this point is df of y is sigma of y times dA of y, okay. And for all of this there is a torque, for each of this element there is a torque, the corresponding momentum is y minus y, is it not, because it will cause a clockwise moment, minus y df. What would be that value? Minus y df is minus y times this, is it not, this is df, that is sigma of y times dA of y. So, essentially if I want to find this total internal torque, I will have to integrate it between the 2 points of interest A and B, some points A and B, I will have to integrate it. So, that will give me y times sigma of y dA of y. and I know that this value is half Fx. How do I know this? From my analysis of statics, I know that this is half Fx. This is Fx by 2. I have already done that part. Okay. And what's more, sigma of y, I have already mentioned in one of the previous, the sigma of y is this, is it not? That is this, capital Y times y by r. Now I am going to use it here. Sigma of y is capital Y times y by r. So going back, that is y times capital Y times y by r. This is sigma of y times dA of y. Okay, that is what I am having here. This is what I am having here. Now, in this, capital Y is the elastic modulus or the Young's modulus, which is the intensive property of the material. Capital R is the radius to which this beam is bent, or the radius of curvature of this bent beam. I can take these two things out because these are constants, and I continue my integration within the limits a and b, right. So, I will get, because there is a y here and there is a y here, this will result in y squared dA of y times this, and this value is half Fx. If I have symmetry, if I have a situation where the top YA is at a distance of d by 2, where d is the width of the beam, and the bottom is at another d by 2, that is essentially I have symmetry, then I can say that this is d by 2 to d by 2, is it not? 0 to d, something like that, or minus d by 2 to d by 2, right, something like that. I can actually define this as the area moment of inertia. This integral y, integral a to b ya to yb y squared dA of y is the so called area moment of inertia. This is different from the regular moment of inertia, the mass moment of inertia that we know, right. This sums the squares of the distances from a plane, whereas the mass moment of inertia sums the squares of the distances from an axis, right. So, this is y squared dA of y. Now, I substitute for IA, substitute for this as IA in this equation, then I will get the bending moment at the section as, because that is minus y by r times IA, is it not? That is the bending moment. So, MB is, the bending moment MB is minus y by r times the area moment of inertia. Now, I can actually relate the magnitude of the curvature as this. Okay. This is the magnitude of the curvature, 1 by r or 1 by modulus r is modulus MB by YIA. What does these two equations relate? These two equations relate 4 quantities, right. What are the 4 quantities? Well, obviously R, MB, Y and IA. What are these? MB is representative of the applied load, applied force. The bending moment is representing the applied load. Okay. The intensive property of the material, is represented through the Young's modulus or the elastic modulus capital Y. Okay. The shape of the material is represented through the area moment of inertia IA, and the response of the beam to this applied load is, or the response of the object under consideration to this applied load is represented by the factor r by the curvature 1 by r by the factor r. Okay. So, these are the 4 things. So, for a given material which has some known Young's modulus y and some known applied load with MB, okay, with bending moment MB, and the material being made of some known Young's modulus y, right. For a given material with MB and y, if the area moment of inertia IA is large, right, then the bending is very small, the amount of bending is small. Or if the area of moment of inertia is small, then the bending is very large. Let us review this one more time. I know that this material is made of some material, that this material is composed of something whose property I know, whose Young's modulus I already know. So, I know capital Y. I also know the applied load through MB. I know both. I know MB, I also know capital Y. Then the relationship is essentially a relationship between the shape of the object, which is IA, and the amount of bending that is seen in the object, which is R, right. For large area or for large area moment of inertia, for large area moment of inertia, bending is very little, and for small area moment of inertia, bending is very high based on this relationship. Now, that means the shape of the object or the area moment of inertia influences to a great degree the amount of bending that is there. If you want to minimize bending, you want to maximize the area moment of inertia. How can you maximize the area moment of inertia? Why is this important? Why are we discussing this? Because we are discussing bending of bones. Why are we discussing that here? Because we have seen in a bone there is cortical bone, a distribution of high amount of mass on the periphery of the bone, and this is called as the compact bone or the cortical bone. And the middle central region is spongy or trabecular cancellous bone, remember. So, where this weight is distributed, it is not merely in the total weight of the bone. Where is this weight distributed makes a difference. Of course, you can have a homogeneous full cortical bone, but per unit mass, per kg, you can only have so much volume, right, because if I am having a homogeneous bone that is fully cortical with no spongy bone in the middle, that will be a very heavy bone, that will be a heavy bone, is it not? You want to have maximum strength per unit mass, per kg of bone, I want to have the maximum strength. That means you want to distribute your mass at the periphery of the bone, and that is what is achieved in this design of this bone, is it not? So, that is why the periphery of the bone has the strong cortical bone or the compact bone, and in the middle you have cancellous bone or the trabecular bone, right. This area moment of inertia is larger when the mass is distributed farther from the central axis or central action, and so because of this reason, for a given bending moment, there is less bending, right. This mass that is far from the neutral axis provides resistance to bending, while any mass that is distributed at the neutral axis practically provides 0 or no resistance to bending. So, the amount of resistance to bending that is offered depends on where the mass is distributed, like the kind of I beams that you see in engineering systems, right. the I beams. Right? These are the so called I beams. I beams, as you see in the picture here, right. These are used in construction and in many other. You can also use solid beams. You can also use solid beams. Why use I beams? You can also use solid beams. Except as engineers, our aim is to minimize the amount of material used while getting the maximum strength benefits. So that means I want to get the benefits of having the full distributed, fully solid beams, but with minimal weight. Because if I have a solid beam, that is going to be very heavy and that is going to be very expensive for me. So this is the reason why long bones such as the femur, for example, are hollow. The central region is going to have the cancellous bone or the trabecular bone or the spongy substance. It is not going to have a lot of mass distributed there. At the periphery, you are going to have a lot of thickness, lot of mass distribution that is happening through the compact bone or the cortical bone. Because per unit mass of the bone, you are going to have maximum resistance to bending that is offered by this design when compared with solid bone. That is, remember, that is, I am not saying that the solid bones will not offer resistance to bending. I am saying per unit mass, per kg of a bone, right. If I have a solid bone of 1 kg and if I have a bone like the regular bone with hollow in the middle and compact bone at the end of 1 kg, the 1 kg bone that is having hollow in the middle will offer more resistance to bending. That is what I am saying. Okay. So, do not misinterpret as saying solid bones are not strong. Solid bones are strong, except that it is more expensive. So, per unit mass of bone you get maximum output or maximum resistance to bending in hollow bones. That is why long bones such as the femur, such as the tibia fibula are hollow. Something to keep in mind and something to think about the design of bones. Right. So, with this we come to the end of this video. Thank you very much for your attention.